A narrow beam of radio light pulses across the darkness, sweeping through the void with the steadiness of a machine that has never known fatigue. Every 22 minutes, a sharp spike rises on instruments built long after the signal first passed Earth. The pattern is so strict that even the smallest drift can be measured. Yet the source sits in a region of stellar evolution where all models say nothing should shine. A star that should be silent is speaking, and it has been doing so since before many of our observatories existed. Picture the first frame. A flat line on a radio chart jumps at perfect intervals, like a heartbeat cut loose from any living body. Another jump comes after 22 minutes, then another. The pattern survives storms, hardware upgrades, and decades of quiet nights. Anyone looking at the data would think of a lighthouse rotating on a cliff. The difference is that this one hangs above the galactic plane, wrapped in cold interstellar dust, far from every structure where new stars are born. You are looking at a corpse that ticks. In the early days, astronomers placed the point on the map of stellar rotation. They expected it to lie alongside slow pulsars that were dimming. Instead, it fell below a boundary known as the graveyard. That boundary is not decorative. It marks the place where a spinning neutron star lacks the energy to ignite the chain reactions needed for radio light. Below it, theory predicts darkness. Yet the beam remains. Why does a dead star insist on behaving like the best clock in the region? What kind of physics lets a dying ember flare in a way that mocks our equations? Our instruments were built to trust steadiness. When a spacecraft sees a metronome that has not missed a beat in more than 30 years, we listen. It is not the power of the beam that unsettles researchers. It is the discipline of its rhythm. A device bolted to a mountaintop should not track a corpse across decades and find perfect repetition. That is why the signal forces a deeper question. If this thing is real, and all evidence says it is, then the universe is running a test of our assumptions. The star is saying something we have not learned to read. A neutron star is small, only the size of a city, cramped into a sphere dense enough to crush atoms into new forms. 1 teaspoon from its surface would outweigh mountains. These facts are familiar to those who study extreme objects. What is unfamiliar is a neutron star that breaks from its class. Most of them spin fast when young, lose energy, slow down, and eventually fade. This source reversed the script. It rotates too slowly to shine by conventional means, yet it sends out a beacon that feels like a challenge. In the first attempts to explain it, teams proposed exotic variants. Some suggested a white dwarf with an enormous magnetic field, though that would require strengths never verified. Others thought of a magnetar cooling after an outburst, but magnetars show high energy light that fades in years, not decades. The source offers none of that. No accompanying glow, no soft tail, no known eruption in the archives. It simply keeps turning on time. The problem is not that we lack ideas. The problem is that every idea fractures when confronted with the details. The signal teaches a subtle lesson. We do not just map the sky, we interpret its logic. If a dead star shines, we must ask whether our categories are wrong. In plain terms, the diagrams we use to sort stellar remnants are built from what we have seen so far, not what the universe is truly capable of. When a new point refuses to obey those diagrams, it exposes the shortcuts hidden inside our theories. It shows how easily we confuse convenience with truth. There is another layer to the mystery. The position of the source sits near a region of the galaxy that is sparsely populated by active pulsars. This emptiness matters. It suggests the object has been drifting undisturbed for millions of years. If it were a leftover from a violent event, its environment should bear scars. Instead, it floats in quiet space, patiently sweeping a beam across the galaxy. It raises a silent question. How long has this clock been running? If it kept time during epochs before our instruments existed, how many signals like it have passed unnoticed? Many cosmic mysteries flicker. They come and go, leaving only a trail of speculation. This one does not flicker. It endures. Human lifetimes are short when measured against the age of the universe. Yet this source has crossed a large fraction of one lifetime without a measurable stumble. Think of that. A star crushed into a sphere no wider than a city has held a rhythm more stable than any mechanical device we have ever launched into orbit. If such stability can arise in the ruins of a massive star, what else might be hiding in the places we have marked as dead? The paradox tightens when we consider energy. A slow spin usually means little power. The chains of particle creation that energize pulsars need speed and strong magnetic twists. This object has neither, at least on paper. Still, the beam keeps forming. It forces us to confront an uncomfortable possibility. Our formulas capture only the behaviors we have been able to calculate, not the full inventory of processes at play inside neutron stars. The interior of such an object may host conditions we have not modeled. We are pushed to imagine layers of physics deeper than the crust and denser than the core. The more one studies the signal, the more it feels like a message from the boundary of our understanding. It is not a message with words. It is a test pulse, a repeatable, steady, defiant pulse that tells us the universe keeps its own accounts of what is possible. Each repetition says that something in our view of collapsed stars is incomplete. If a single object can subvert the line between active and dead, others may be doing the same without drawing attention. It makes us ask, what if the cosmos is full of quiet structures performing roles we have not yet recognized? This first glimpse shapes the path ahead. The radio beam is just one clue among many. It links to stranger signals waiting deeper inside the map of stellar remnants. To follow them, we must treat this object as the first doorway. Its light shows a corridor leading toward regions of research where assumptions must be set aside. To move forward, we commit to listening in new ways, to letting the data decide what a dead star can or cannot do. If this one beacon can overturn a theory built through decades, what might we uncover when we examine the other signals that rise from the galaxy? If cosmic mysteries speak to you, like and subscribe to the Quiet Universe channel. The first clue did not arrive as a dramatic spike or a blinding flare. It appeared as a small, disciplined rise on a radio plot, the kind of detail that could have been lost in system noise if someone had been less patient. The line climbed, fell, then settled. 22 minutes later, it climbed again. In the offices where long-term survey data is checked, nobody gasps at first. Pulses come and go. Many are false alarms. Yet this one remained even when old recordings were reviewed. The same signature had been hiding in plain sight for decades, stable enough that a careful hand could overlay the pulses from different years and see them line up. To understand why this matters, imagine a neutron star as a collapsed furnace. It was once the heart of a massive sun, burning through its fuel until gravity overwhelmed it. Then came collapse. Outer layers exploded. The core shrank to a sphere only a few tens of kilometers wide. Inside that sphere, pressures crush atoms and pack particles together in a state that defies ordinary chemistry. Most neutron stars that still shine are young and fast. They rotate many times per second, flinging narrow beams of radiation from their magnetic poles, but rotation slows with age. Eventually, a point is reached where the engine sputters and the beams vanish. That region is sometimes called the graveyard, and on any chart it marks the place where pulsars go dark. The new object sat below that line. It rotated too slowly to generate the conditions needed for radio light, yet the beam was there, ticking with the reliability of a laboratory clock. Even students who had learned the theory for the first time could tell there was a contradiction. It was like hearing footsteps in a sealed room. If the star was too slow to create the cascade of particles that power a beacon, what was feeding the light? The mismatch between prediction and measurement became the spark that lit this investigation. The clue deepened when researchers plotted its drift. Pulsars typically show some irregularities due to internal stresses or changing magnetic conditions. They may glitch, slipping in rotation. They may slow down as energy leaks into particle outflows. This one was different. Its period change was so mild that it could be measured only by comparing widely separated measurements. It was steady in a way few neutron stars manage. The steadiness is the problem because a dead star should not shine, and a shining star should not be this calm. What kind of mechanism produces such a neat contradiction? Looking deeper into the data, teams searched for supporting signals. High-energy telescopes scanned the region for X-rays that might indicate a magnetar cooling after a violent episode. That would be a possible source for radioactivity at slow rotation. But the sky around the object remained quiet. No long-lasting glow, no aftershock. The silence ruled out some of the simplest explanations. There was no sign of a recent eruption, no trace of accretion from a companion star. It sat alone, unaffected by neighbors, yet pulsing with confidence. One image stands out: a rotating sphere, tiny against the background of the galaxy, swinging a beam like a silent lighthouse. There is no water below, only the thin fog of interstellar gas. The beam cuts through that fog and crosses unimaginable distances before striking a detector on Earth. We watch each swing and try to match it with theoretical expectations. But the model we have built says that such a lighthouse should be off. The contradictions pile up. If the region on the diagram where the star lives is labeled as silent, then the diagram is wrong, or the star is unlike any that we have studied. Visual anchors help the mind grasp scale. Imagine the city you live in. Now compress it into a sphere that could fit inside a lake. That is the approximate size of a neutron star. Inside that compact object, forces twist magnetic fields into shapes we struggle to simulate. A single charged particle moving along a field line near the pole can set off a cascade of photons. Those photons form the radio beam, sweeping across space. But for the beam to form, rotation must be strong enough to accelerate particles. In slow rotators, acceleration fades and the cascade collapses. The boundary between active and inactive pulsars is not an arbitrary border. It is a physical threshold. Crossing it should extinguish the beam. The object ignores that threshold. We have to consider alternatives. Some have proposed that the magnetic field might be unusually strong, perhaps bridging the gap created by slow rotation. Others suggest that the interior of the star might host superconducting or superfluid regions that alter the magnetic geometry in unexpected ways. There are even speculative ideas about buried fields rising to the surface over long timescales. None of these ideas can be dismissed outright, but none fully explain the precise timing of the pulses and the absence of supporting high-energy signals. The star refuses to fit the shape of any theory placed around it. There is a path that scientists often walk when faced with such anomalies. First, distrust the data. Teams check for instrumental errors, clock malfunctions, software bugs, or contamination by satellites. Those checks were done. Nothing in the hardware could account for the repetition. Then, distrust the interpretation. Maybe the object is not a neutron star. Could it be a strange white dwarf with a magnetic field larger than any measured? That path has been explored, but the necessary field strength would push the limits of what such stars can sustain. Once both avenues run out, the anomaly remains. The data persists. It leaves a mark on every mind that confronts it. The human element of this search adds another dimension. Picture a researcher staring at a fold of archival data from the 80s. They notice the same 22-minute interval that appears in the newest observations. A quick calculation reveals that the pulses have aligned for almost half a lifetime. It is an experience that feels like talking to a patient storyteller. The star has been speaking with a steady voice while generations of technology have come and gone. It does not shout. It repeats the same line until someone listens. At the heart of this chapter lies a question. What is it about the interior of a neutron star that allows for surprises like this? The physics of matter at nuclear densities is not fully mapped. Even the crust is a labyrinth of exotic phases. Beneath it lies a soup of neutrons and possibly other particles arranged in forms we have barely considered. The magnetic fields thread through those layers, and rotation stirs them into patterns. A phenomenon we think of as simple, like a beam of radio light, may depend on mechanisms we have not learned to describe. The object that shines below the graveyard line may be the first clear sign that our models lack crucial ingredients. This leads to a broader reflection. When we draw a line on a diagram, we forget that nature does not see our diagrams. The universe is not obligated to obey the boundaries we sketch. A star that should be dark can shine if conditions inside it differ in some vital way from our assumptions. That possibility forces humility. It means that every neat category in our textbooks is provisional. It also means that the cosmos is richer than the tidy structures we impose on it. Another human-scale thought intrudes. On Earth, we build clocks that drift, we build machines that fail, we recalibrate instruments because heat, cold, and the passage of time affect them. Yet here is an object made of crushed matter, born in a blast, left to cool in the emptiness between spiral arms. It should be chaotic, unpredictable, perhaps silent. Instead, it keeps time better than our precision devices. It is a strange feeling to watch something so alien act with such discipline. It reveals how shallow our intuition about extreme environments truly is. Slowly, we return to the central tension. A star that should not shine is shining. A corpse is acting alive. A clock buried in the sky keeps better time than our own. What emerges is not just a mystery about one source. It is a pressure on the entire framework we use to understand neutron stars. If one object sits below the graveyard line and pulses, others might be waiting. How many unrecognized beacons sit in the archives, dismissed as noise? How many borderline cases have been thrown out because they did not fit the neat profiles we expected? We must consider the faint possibility that the boundary between life and death for neutron stars is more porous than we thought. There may be transitional states, slow rotators that manage to generate beams through mechanisms we have not cataloged. There may be long-lived magnetic structures hidden beneath the crust, ready to channel charged particles even when rotation weakens. There may be conditions that allow a star to flicker back to life after drifting into the graveyard. These ideas are speculative, but the data invites speculation grounded in evidence. As we look ahead, this dead star that refused to die becomes more than a curiosity. It becomes a foundation. The next steps move from this contradiction to deeper questions about what neutron stars can do when they break the rules we have drawn. The first chapter left us standing before a contradiction, a dead star shining where no light should be. Now we step inward, into the engine room of that impossible glow. We begin at the surface, where crust and magnetic field meet in conditions that compress familiar physics into something sharper. A neutron star is not hot in any ordinary sense. Yet around its magnetic poles, a kind of flame forms. It is not a fire made of heat or burning gas. It is a storm of charged particles pulled into violent motion by fields strong enough to bend the paths of photons. This is the cold flame, a jet of radiance born from forces that should have been spent long ago. To see this flame, imagine following a single electron on the surface. It is trapped by magnetic field lines that rise from the interior and curve outward like rigid wires. As the star rotates, those field lines sweep space, dragging charged particles along with them. When a particle moves along a curved field line, it emits radiation. That radiation seeds more particles. The effect cascades, multiplying into a torrent of light. This cascade is the reason young pulsars shine. It is a delicately balanced process. Slow the rotation too much. Weaken the magnetic geometry by a small amount, and the cascade collapses. Yet in this star, the flame persists. In laboratories on Earth, we cannot reproduce such conditions. Our magnets are insignificant by comparison. Our particle accelerators struggle to mimic even fragments of the electric fields near the poles of a neutron star. Still, mathematics gives us a foothold. We model how electrons should move, how photons should split into pairs of charged particles, and how those particles trigger further emissions. What emerges is a picture of a flame that burns without consuming fuel. It draws energy from rotation and magnetic tension. When those run out, the flame should die. But here, in this anomalous star, the flame has refused to dim. One visual analogy helps anchor this idea. Think of a snowy mountain slope where a single disturbance can trigger a cascading fall. The cold flame resembles such an avalanche. One electron sets off a chain, and the chain multiplies. But for an avalanche to continue, the slope must be steep. In our star, the slope, if one can call it that, should be too gentle. Rotation is slow, magnetic fields appear insufficient, and yet the avalanche continues. What holds it steady? Is there a hidden channel in the magnetic field that keeps the cascade alive? Observations hint at clues. The light from this star seems polarized. When radiation is polarized, the waves line up in a preferred direction. That preferred direction usually reflects the geometry of the magnetic field. Some measurements even suggest that the alignment flips abruptly as the beam sweeps across Earth. A flip can include a 90-degree shift, a sign that we are looking directly into the core of the particle cascade. These flips are fingerprints, each one marking a place where the cold flame twists. Nothing about these patterns suggests a dying engine. They suggest precision. The contradiction grows sharper. Polarization flips imply active, stable emissions. Active emissions imply a robust cascade. A robust cascade implies rotation and fields above a threshold that the diagrams say is unreachable in slow rotators. If the object sits below the graveyard line, why is the flame behaving like that of a young pulsar? What force is shaping these beams? What reserves of energy remain inside the star? How many other stars inhabit this hidden domain where theory has yet to look? We must visit the inner crust. Inside the star, matter forms layers with exotic names. One layer may resemble a lattice of nuclei squeezed into shapes that look like sheets. Another layer may form rods. Deeper still, neutrons may flow like a superfluid. As rotation slows, this interior may shift, storing tension that later rises to the surface. If that tension is released along the poles, it could strengthen magnetic channels. In such a scenario, a slow rotator might still support a narrow flame. Yet this idea demands precision and timing. The star would need to maintain a delicate configuration that stays stable over decades. This stability shows in the timing of the pulses. If the star were releasing energy unevenly, the beam should wander or drift. Instead, it remains locked. Many stars shake as they cool. They crack, they shift, they glitch in rotation. The cold flame star shows almost none of that. It is a sign that the interior is calm. That calmness is strange. A star that should be losing energy appears instead to be conserving it. Is it possible that the object has entered a plateau, a long-lived state where rotation slows so slowly that the flame remains perched near threshold? Consider now the line of sight from Earth to the star. As the beam sweeps across us, we catch only a thin slice of the cascade. If the beam's core is narrow, even small changes in geometry could lead to large changes in signal. But the signal does not change. It suggests that whatever mechanism powers the flame is not just persistent but geometrically stable. Field lines hold their shape. Particle flows remain orderly. The route from crust to space is open. This is unusual. The cold flame is not flickering. It is structured. At this point, a difficult idea enters. Perhaps the boundary between active and dead pulsars is not sharp. Instead of a single graveyard, there may be a plateau or series of ridges where slow rotators find ways to shine if their magnetic geometry traps pockets of energy. The cold flame becomes a signpost marking one of these ridges. It suggests that the energy landscape inside a neutron star contains unexpected peaks, small regions where conditions briefly mimic the behavior of much younger stars. In such regions, a cascade might form even with slow rotation. What could carve such ridges? One possibility involves buried magnetic fields. Over long timescales, fields trapped in the crust could drift upward, re-emerging like roots breaking the surface of a frozen lake. As they rise, they could twist existing field lines, creating channels where acceleration is still possible. Elevated channels would focus energy into narrow regions. If the star rotates slowly, Those channels might open only occasionally, but when they do, they might feed the cold flame. Another possibility invokes the superfluid core. Superfluids rotate differently from ordinary matter. They form arrays of vortices. If these vortices move or interact with the crust, they could alter the rotational energy budget. They could lend stability to the beam, anchoring its rhythm. Some models hint that interactions between superfluid vortices and magnetic structures could trigger small but persistent emissions. If so, the cold flame would be a surface expression of deeper motions within the star. We return now to the light itself. Spectra of the beam show that the emissions are narrow. Narrow beams are hallmarks of strong field lines. But strong field lines are not expected in stars that have aged beyond their active phase. This forces us to consider whether the star might be older or younger than we think. If it were young but spun down unusually fast, perhaps through a past interaction with its environment, it could retain strong fields even when rotation slows. If it were old but preserved by some internal mechanism, it might have avoided the decay seen in other stars. Every option carries complications. A young star with rapid spin down should show signs of disruption. An old star with preserved fields should show signs of internal heat or external activity. The observed quietness undermines both. It leaves the cold flame star in a narrow corridor between these extremes. A corridor is fitting. It matches the idea of a flame burning in a tight channel. We picture a bright path, defined by forces we cannot see, threading through matter so dense that a handful of it would outweigh a cliff. The closer we look, the more the cold flame becomes a metaphor for the entire study of neutron stars. It is a phenomenon that glows without heat, that persists without obvious fuel, that burns rules as much as it burns matter. Scientists measure angles, timing, polarization. They compare with catalogs of pulsars known to behave properly. This star sits outside those groups, challenging classification. It reminds us that science often advances when a stubborn object refuses to fit the boxes prepared for it. We must also reflect on scale. On Earth, a flame requires oxygen and fuel. It flickers in response to wind or temperature. The cold flame on a neutron star needs none of those things. It is immune to weather. It exists in a vacuum. It is immune to small disturbances. It burns with an indifference that dwarfs our experience. When we call it a flame, we do so to give ourselves a foothold. The underlying reality is a structured emission of electromagnetic radiation driven by quantum processes. It is delicate yet immortal compared to our fires. What matters most is that the cold flame defies expectations built from decades of observation. It compels us to redraw the graveyard line, to reconsider the thresholds of rotation and magnetism. It opens the possibility that many stars in the supposed graveyard could host hidden flames. If we tune our instruments to search for slow, faint pulses, we might discover an entire population of cold flame pulsars. That population could reshape our understanding of stellar death and the life cycle of massive suns. As we leave the inner workings of the flame, one thought echoes. If the cold flame thrives in a place where no fire should burn, then the outer reaches of neutron star behavior may be stranger than any current model allows. Long before the dead star that refused to die unsettled the diagrams, another remnant had been carrying on a stranger habit. It drifted through space almost silently, a runaway ember from an ancient explosion, and yet the region around it glowed in gamma light. That glow puzzled observers because the star itself was quiet in radio wavelengths. There was no ticking beam, no steady rhythm. Instead, the space behind it shimmered with a diffuse haze, the kind created when particles with enormous energy collide. This haze hinted at something unexpected: antimatter, drifting outward from a neutron star that seemed otherwise asleep. To appreciate why this matters, imagine a faint body moving through the galaxy. It leaves no trail the eye can see, but instruments detect particles that behave unlike the common cosmic rays arriving from far away. Detector readings show positrons, the mirror particles of electrons, appearing in greater numbers than expected. These particles do not survive long. When they meet normal matter, they vanish in a burst of light. For detectors aboard spacecraft orbiting Earth, such bursts mark the presence of antimatter. As the data accumulates, one question grows sharper. Where are all these positrons coming from? The puzzle deepens because antimatter is not plentiful in our part of the galaxy. Ordinary processes produce a small amount. Collisions of cosmic rays with interstellar gas generate some. Certain energetic events produce more. But the surplus observed near Earth is too large to dismiss. It demands a source. For a time, some researchers wondered whether exotic particles, perhaps linked to dark matter, could be decaying into positrons. That idea carried weight because the distribution of the detected positrons seemed difficult to explain by known sources alone. Yet when gamma maps of the sky improved, they revealed something else. A star near our neighborhood was surrounded by a vast cloud of high-energy light, a signature pointing to one culprit. This culprit was a neutron star known for its silence. It had no obvious radio pulses, yet it sprinted through space with notable speed. Its path, if traced on the sky, would show it crossing an angle similar to the width of the moon given enough time. The star was old. The environment around it was sparse, and yet the region behind it blazed in gamma rays, as if a powerful wind were blowing out of the star and striking the gas around it. In that collision, particles would be accelerated, producing the light that our instruments detect. More importantly, that acceleration could create streams of positrons. Imagine the star as a dark coal gliding across a field of dust. If you struck that coal with a charged particle, a faint spark might jump. In the case of this neutron star, the whole region lights up. The star's magnetic field, though no longer driving a bright pulsar beam, still organizes surrounding matter into a shock. The shock acts like a bow formed by the star's motion. Charged particles become trapped, accelerated, and cast into space at extreme energies. These accelerated particles then decay or interact, producing positrons. It is a complicated process, but the chain leads from the neutron star to the detectors circling Earth. A visual anchor helps. Picture a knot of light in the gamma sky, a patch brighter than the surrounding darkness. That knot is not a star shining in traditional wavelengths. It is a halo of emissions produced when energetic particles crash into the interstellar medium. The halo can be larger than familiar constellations. It sits near the path of the runaway neutron star. As the data sharpen, calculations suggest that this halo alone could, under certain assumptions, account for a large fraction of the positrons arriving at detectors near Earth. This is a profound shift. It means that at least part of the antimatter trail haunting our region may be nothing more exotic than the breath of a quiet neutron star. Why would a neutron star that appears dead in radio still drive such a powerful wind? Neutron stars remain magnetic long after their rotation slows. While radio beams may cease when the cascade weakens, the underlying fields persist. These fields can continue to accelerate particles, though less efficiently than in young. Bright pulsars. A moving neutron star plows through the gas and dust around it. This plowing compresses and heats the gas, setting up a shock. In the shock, particles are accelerated to extreme energies. The star becomes a silent accelerator. It does not shine with a beam, but casts a wide, diffused trace. The antimatter trail grows with time. As the star moves forward, more particles join the stream. Some diffuse into interstellar space, some drift toward our region, and some strike detectors. The scale of this trail is enormous. If we could see it with our eyes, it would span an area far larger than any feature we recognize in the night sky. It is a reminder that neutron stars, even when invisible in ordinary light, shape the galaxy's particle ecosystem. They are engines that run on long memories, echoing the violence of their birth millions of years later. One question rises. If a quiet neutron star can flood our part of the galaxy with positrons, how many others might be doing the same? The Milky Way contains thousands of neutron stars. many of which have not been catalogued. Some are too faint. Some never pass through the beam geometry that would make them visible as pulsars. Others may hide behind dust. If each contributes even a small amount of antimatter to the galaxy, the combined effect could be significant. The antimatter excess near Earth may be a simple result of living in a galaxy full of compact remnants. Yet we must be careful. The distribution of positrons measured by instruments is not uniform. It peaks at certain energies. It falls at others. The spectrum carries clues about the sources. While a neutron star shock can produce positrons, matching the observed spectrum requires detailed modeling. Some models suggest that a pulsar wind nebula, even one without a strong radio signature, could fit the data. Others propose that multiple neutron stars scattered through the plane contribute. A single source might be insufficient, but the silent star with the gamma halo stands out as an obvious candidate. A deeper look at the halo reveals structures. The brightness may vary across the region. Certain edges might appear sharper. These features could reflect the geometry of the shock and the movement of the star. They might also reflect how particles diffuse. Diffusion in space is complex. Magnetic fields guide particles along routes that can twist and turn. Positrons might wander along field lines, taking long roads toward Earth. Their arrival pattern would then reflect not just the source, but the network of fields between us and that source. This idea brings us to a human-scale analogy. Imagine a perfume released in a crowded city street. People far from the release point smell it in subtle waves. The scent arrives in bursts, carried by the wind and shaped by alleys. Likewise, positrons wander through the galactic neighborhood, following lines that we cannot see. Instruments catch them long after they were created. The halo is the origin. The detectors are the noses. Between them lies a labyrinth of unseen corridors. But the antimatter trail is not only a curiosity about particle physics. It reveals something about neutron stars as long-term agents. Even when silent, these stars continue to sculpt their surroundings. Their winds enrich the medium with particles that may influence chemical and physical processes in diffuse gas on much larger scales. Such winds contribute to the background emissions of the galaxy. They fill space with aftershocks of ancient explosions. The antimatter trail is one of those aftershocks. We then confront a philosophical point. When we measure unusual positron levels near Earth, the instinct is to look for exotic physics. It feels compelling to imagine new particles or new forces at work because mystery invites grandeur. But nature often chooses simpler mechanisms. A quiet star, moving through space with nothing to draw attention, can produce a trail rich enough to confuse detectors. It is a humbling reminder that not all mysteries require new laws. Some require only a deeper look at familiar beings. Still, the door to the exotic remains open. Certain aspects of the positron distribution do not align perfectly with a single neutron star origin. Some researchers argue that the data suggests multiple sources. Others suggest that a mixture of processes is at play. We cannot close these possibilities. But the existence of the gamma halo provides a grounded explanation for at least part of the antimatter. It reduces the need for drastic revisions. It shows that neutron stars, in their quiet phases, hold power long after we expect them to fade. A final piece of the puzzle comes from kinematics. The runaway neutron star moves with great speed. Its velocity hints at the explosion that launched it, during the supernova that birthed it. Asymmetries in the blast imparted a kick. That kick set the star on a lonely path. As it sped away, its wind interacted differently with the gas around it. The shape of the halo reflects this motion. Just as a boat forms a wake, the neutron star forms a wake of particles. In that wake lies the antimatter trail. Now consider the scale of its journey. Over thousands of years, the star has crossed vast stretches of space. The trail it leaves behind mixes with the local medium, spreading outward. What reaches Earth is not a direct beam, but a diluted, wandering stream. Yet even diluted, it is detectable. That alone testifies to the strength of the source. For a particle emerging from the shock to survive a journey of such distance and still be measured is no small feat. It highlights the efficiency of the acceleration mechanism. As we stand at the edge of this chapter, the meaning becomes clear. Neutron stars are not simply dead cores drifting in silence. They are dynamic agents that shape the galactic environment. Some shine with cold flames. Some pulse in ways that defy death. Some carve antimatter trails through the darkness. The silent star with the gamma halo reveals a truth. Even absence of a pulse does not imply absence of influence. What we see as quiet may be only a limit of our eyes. If quiet neutron stars can fill the sky with antimatter, then the next step is to explore how their silent winds reveal deeper patterns in the galactic web. The clues gathered so far point to a quiet truth. Neutron stars do not merely shine or fade. They measure. They imprint their rotations on spacetime itself. When a pulsar spins, its beam sweeps outward with such regularity that we can predict the arrival of each pulse to extraordinary precision. This precision becomes a tool. If the pulse arrives early or late by even a few hundred nanoseconds, something has shifted the distance between us and the star. A disturbance has passed along the line of sight. That disturbance can be gravity itself moving as a wave. To understand this, imagine dozens of pulsars scattered across the galaxy, each with its own rhythm. They make a lattice, a quiet geometry of ticking nodes. Every tick travels to Earth across light years. If space-time stretches slightly between Earth and any pulsar, the tick arrives late. If space-time contracts, the tick arrives early. These early and late arrivals create patterns. When scientists place the patterns from many pulsars side by side, they form a grand design, a map of ripples passing through the Milky Way. These ripples are gravitational waves of a different kind than the ones caught by ground-based detectors. Instead of the quick bursts produced by colliding neutron stars or black holes, these waves are long and slow. Their wavelengths can span light years. They form a background hum, the deep voice of heavy objects spiraling around each other over millions of years. It is not a single event, but the combined chorus of countless mergers and interactions. Some may even trace back to early cosmic epochs, after the universe cooled but before galaxies formed. The pulsar network becomes a watchtower for these waves. Each pulsar stands like a distant bell struck by the universe. The bells ring steadily. What we measure is not the bell itself, but the pattern of its ringing. When one bell is delayed and another arrives on time, we note the difference. When many show the same kind of shift, a pattern forms. The pattern is the signature of a passing gravitational wave. It has a shape predicted by the mathematics of general relativity. The shape points toward a fundamental truth. Even in the calm night sky, space-time is restless. A visual anchor makes this idea clearer. Picture a pond at dusk. Stones drop into the water far from shore. Their ripples spread outward, overlapping and colliding until the surface seems still. Yet if you float a tiny leaf on the surface, it moves gently in response to ripples too faint for your eyes. The pulsars are the leaves, and the detector on Earth is the watcher. Every slight shift in rhythm is the leaf responding to a wave from somewhere in the pond of the universe. What surprises researchers is how coherent the pattern becomes when enough pulsars are included. A single pulsar can be influenced by local noise. Its pulse might wander slightly due to internal processes or surrounding plasma, but an array of pulsars, when taken together, reveals harmony. Their combined timing shifts match a curve predicted decades ago. The curve suggests that the Milky Way is being shaken by the slow dance of giant black holes orbiting each other in distant galaxies. It is the first time humanity has gained evidence for these long waves. We return to the neutron star as a tool. It does not produce gravitational waves in this measurement. It senses them. Its rotational precision transforms it into a probe of space-time. The star spins, beams its light, and waits for the universe to tug on the distances involved. It keeps time as an archivist might, recording quiet shifts across eons. When dozens of these archivists agree that spacetime has stretched by a tiny fraction, we accept the record. The precision involved is almost impossible to imagine. A pulse from a distant pulsar may arrive a few hundred nanoseconds earlier than expected. That tiny difference, smaller than the blink of an eye by orders of magnitude, is enough to reveal the presence of a wave larger than a star system. This juxtaposition stretches the mind. Human devices struggle to maintain accuracy on such long baselines. Yet the galaxy hosts machines of nature that maintain their rhythm over centuries. There is a pattern inside the pattern. The direction between pulsars matters. Pulsars separated by certain angles show stronger correlations in their timing shifts. Others show weaker ones. When plotted, this angular correlation forms a distinctive curve. The curve is the fingerprint of a gravitational wave background. If a different mechanism, such as local plasma variations or clock errors, were to influence the pulsars, the curve would not appear. But it does. With each new pulsar added to the network, the curve sharpens. One can imagine this watchtower standing over the galaxy. Each pulsar is a post. Each pulse is a flag waving in the wind of space-time. We watch thousands of such flags. Together, they reveal the wind, even if it is too faint to feel directly. This is the essence of the pulsar timing array. It is not an observatory in the usual sense. It is a distributed instrument, stitched from the dead cores of stars. It is a reminder that even the remnants of cosmic violence can serve as sentinels. We must acknowledge uncertainty. While the evidence for the background hum is compelling, we do not yet know the exact mix of sources. The waves may come from pairs of giant black holes slowly spiraling inward. They may include contributions from other processes imagined, but not confirmed. Some suggest that the texture of space-time itself, shaped in the early universe, could add a faint note to the chorus. These ideas remain open questions. The watchtower listens, but does not yet translate. A human-scale comparison offers perspective. Imagine trying to detect a shift in the distance between two cities by measuring the timing of traffic lights in one of them. You would need incredible precision. Yet the timing array does something even stranger. It measures changes in distances across thousands of light-years by observing pulses from stars the size of cities. The feat is a triumph of patience and careful analysis. The strength of the watchtower lies in its network. One pulsar is a timepiece. Many are an instrument. When their pulses are combined, the galaxy becomes a lab. Each pulse is a clue. Each delay or advance is a hint. Over years and decades, the hints accumulate. Eventually, they reveal a message. The message is simple. Space-time is not still. Something massive far away is stirring it. Now the chapter arrives at its central reveal. The pattern measured across the pulsar lattice matches the predicted shape of a gravitational wave background. It is the first large-scale evidence that heavy objects in distant galaxies are carving slow rhythms into space-time. Rhythms so deep and stretched that only the galaxy's most stable clocks can hear them. When gravity's long waves become clear in the data, like and subscribe to the Quiet Universe channel. What this means is that the dead stars we thought of as silent are actually hearing the heartbeat of the universe. Their pulses carry the imprint of distant titans spiraling together. They are the ears through which we sense the slow music of space-time. The watchtower has opened, and through it we glimpse an invisible architecture of motion that fills the cosmos. If pulsars can reveal the gentle sway of space-time itself, then the next step is to follow the signals that flare and fade far faster in the fleeting blue flashes of cosmic transients. Before the pulsar watchtower could settle into its role as a listener of deep rhythms, another class of signals erupted across the sky that refused all sense of order. These events were short. They were violent. They appeared without warning in galaxies and in the empty spaces between them. When telescopes first caught them, the flashes burst into view brighter than whole galaxies, then began fading before the observing software could finish logging the initial alert. They were blue, sharp, and fast. They defied every pattern familiar to stellar death. One such flash erupted within reach of our wide-field surveys. The detectors were scanning for asteroids when a point of light leapt into existence. In the first moments, it shined with a brilliance that eclipsed supernovae. Yet instead of lingering for weeks as normal explosions do, this flare fell in brightness within days. The decline was too quick. The spectrum was too blue. The energy release was too concentrated. No known supernova behaved this way. It seemed as though the universe had struck a match in a vacuum and then snuffed it out before we could look closely. These flashes were eventually grouped under a name describing their behavior. The label is less important than the nature of their defiance. A supernova occurs when a star collapses or when a white dwarf accumulates too much mass. Both processes create predictable light curves. They brighten, plateau, then fade. But these blue transients brighten much faster. They show a rise so steep that it challenges every model of diffusion through stellar material. They fade far faster than the radioactive decay expected from normal elements. They leave behind almost nothing. It is as if a star exploded without leaving a corpse or a glowing remnant. Take a visual anchor. Imagine walking across a dark field. In the distance, a camera flash goes off. For an instant, the world is clear. Then it is dark again, and you cannot find the source. These transients behave like that. They give us a moment of clarity and then vanish into the broader darkness. The sky holds no afterglow that fits conventional expectations, no clear sign of a shockwave expanding through gas, no lingering cloud, only a fading memory that begins to decay the moment we look. The locations of these events deepen the mystery. Early flashes were found inside galaxies, but not where massive stars usually die. Some appeared in regions with few young stars. Others appeared far from any recognizable structure. One flash, observed with growing confusion, erupted between two galaxies. That position made no sense for a massive star's death. Massive stars do not drift alone in the abyss. They form in clusters and die nearby. The intergalactic flash hinted at a source that did not match any known population. Researchers wondered whether something else entirely might be exploding. When interpreting the flashes, several lines of thought emerged. One idea proposed that these were unusual types of core collapse events, where the star had lost almost all of its outer layers. If so, the remaining core would explode quickly and cleanly, producing an intense but short-lived flare. But such a stripped core would usually be found near a companion star that helped remove those layers. Many of the flashes showed no evidence of such companions. Another idea considered the possibility of a failed explosion with a jet that broke through the star. But jets usually leave traces. We did not see them. A more adventurous idea suggested that intermediate mass black holes, if they exist, might tear apart stars that stray too close. The ripping of stellar matter could release energy in short, bright bursts. But this scenario demands black holes of masses not yet firmly proven. It also requires stars to wander near them in places where stars are rare. The pieces did not fit comfortably, yet the absence of alternatives kept the idea in circulation. Some flashes seemed to carry signatures that resembled partial tidal disruptions, though no consensus had formed. The physics of these flashes is challenging. To produce such luminosity, a large amount of energy must be released very quickly. To produce such a blue color, the emitting material must be extremely hot. To fade so fast, the material must be thin. Thin material would let light escape easily, reducing the diffusion time, but thin material would also mean that only a small amount of mass was involved, which contradicts the brightness. These competing conditions produce a tension. How can a small mass produce such vast luminosity? How can an object become so hot and then cool so quickly? One scenario considers shock breakout. When a shock wave from a collapsing star reaches the surface, it produces a brief burst of light. In a normal supernova, the shock breakout is often overshadowed by later emissions. But if the star has lost most of its layers, the shock breakout might dominate. This could produce a fast, ding, bright signal, yet it would still require a star in a plausible location. The intergalactic flash resists this. How does a star lose layers while floating between galaxies? Another scenario imagines a merger. A neutron star and a massive companion could merge and produce a violent flare. Mergers can create intense emissions. They can also produce jets. But mergers leave a fingerprint in gravitational waves, and no such signal was detected at the time of these flashes. Without a matching gravitational counterpart, the merger scenario becomes speculative. It remains possible but unproven. The flashes do not give their origins easily. A human-scale analogy might help. Imagine a firework that goes off in the middle of a desert with no smoke trail, no debris, and no sound. All you see is the light. You walk to the place where it happened, and the sand is untouched. That is the experience of chasing these blue transients. We detect them above us. We look again, and they are gone. By the time the telescopes turn to study them, the afterglow has already dwindled. Some flashes show subtle differences. One flare might show a rapid decline, but leave faint signatures of heavy elements. Another might show no such trace. These differences divide the group into possible subclasses, but classifications are fragile. When events are rare, every new observation risks reshaping the categories we build. For every pattern found, another breaks it. This is why some researchers think we are looking at more than one kind of explosion. The sky might be giving us samples from multiple rare processes. What complicates matters further is that many flashes appear in galaxies with low rates of star formation. This contradicts the idea that they are linked to young, massive stars. If a galaxy is not producing large numbers of massive stars, it should not produce frequent exotic supernovae, yet the flashes appear there. It suggests either that the progenitors live long and drift into quiet regions, or that entirely different objects are at work. Compact remnants, perhaps? White dwarfs interacting with unseen companions. Neutron stars stripping passing matter in unusual ways. As we map these events, a pattern of frustration and fascination emerges. We know they are bright. We know they are fast. We know they sometimes erupt in places no ordinary star should die. But we do not know what triggers them. Each flash feels like a clue ripped from a larger text, a piece of the puzzle that does not yet have surrounding edges. Researchers gather the pieces and try to assemble them, but the image remains incomplete. One reason these events matter is that they challenge our understanding of energy release in stellar systems. If matter can convert energy this quickly under certain conditions, those conditions must be identified. If new pathways to stellar death exist, they must be mapped. These pathways influence the distribution of heavy elements, the formation of compact remnants, and the balance of forces in galaxies. The flashes are windows into processes we do not yet understand, processes that could shape the galactic environment at multiple scales. Another reason they matter is that they expand our imagination of what compact objects can do. We have seen neutron stars emit beams. We have seen them accelerate particles. We have seen them sense gravitational waves. Now we see violent flares that might be tied to compact remnants as well. The cosmos may be experimenting with forms of energy release that occur only in rare corners of parameter space. If so, the blue flashes are signatures of those experiments. Consider now the intergalactic flash again. Its loneliness is striking. A flare bright enough to outshine galaxies for a moment, occurring in the dark bridge between them. Such an event forces us to question our assumptions about where stellar remnants can travel. Could a star have been flung from its galaxy by gravitational interactions, then aged in solitude until some final instability ignited it? Could two remnants have met by chance? These questions remain open. The flash stands as a reminder that the universe is not bound by the tidy borders we draw on star charts. As telescopes improve, more of these flashes appear. Each new detection adds a point to a growing constellation of anomalies. The sample is still small, but the hints are unmistakable. Something in the universe produces fast, blue, luminous flares at a rate that cannot be ignored. These events force theorists to stretch models in new directions. Perhaps a new class of compact object interactions is at work. Perhaps our understanding of mass loss in late-stage stars is incomplete. Perhaps entirely new processes lie beneath the data. Yet in all of this uncertainty, the flashes share a common trait. They are brief. Their brevity gives them power. They reveal conditions that exist for moments, then collapse. Such moments are precious because they show us physics under extreme compression. They offer glimpses into states of matter and energy that no laboratory on Earth can match. Each flash is a message written in light from deep inside a dying or transforming object. The message says that the universe continues to surprise. If stars can erupt in places where none should exist, and if their flashes vanish before we can fully grasp them, then the next step is to consider how all these impossible signals weave together into the larger maze of collapsed suns. The map is crowded now. A dead star that refused to die. A cold flame burning without heat. A silent wanderer spreading antimatter through its wake. A watchtower of pulsars hearing the slow breath of spacetime, and blue flashes erupting from nowhere. Each signal is strange on its own. Placed together, they form something more unsettling. They outline the entrance to a labyrinth, a maze woven from contradictions, threaded with remnants that defy the clean categories we drew in books. As we enter this maze, the familiar structure of stellar evolution dissolves. Neutron stars, once treated as predictable endpoints, become actors with many roles, each revealing a different corridor of the labyrinth. The first corridor is defined by impossible persistence. The 22-minute beacon pulses from a region where no star should shine. It stands like a locked door with a light leaking under the threshold. The cold flame opens another. Its particle cascade burns in a place where rotation should be too slow. These two corridors run parallel for a while, hinting at an internal mechanism we have yet to identify. Then the antimatter trail curves off to the side. A silent neutron star blows a wind strong enough to paint the sky with gamma rays, revealing that even a quiet remnant carries hidden force. Meanwhile, the watchtower corridor rises upward. Pulsars form a high structure that detects gravitational waves stretching across the galaxy. And the blue flashes, far from any such neat geometry, streak across the maze like lightning bolts, illuminating corners where no star should stand. What are we to make of this? How can a single class of object generate such diversity in behavior? The first answer is that neutron stars are not simple objects. Their interiors hide phases of matter unknown elsewhere. Their magnetic fields pierce space with a strength unmatched by anything on Earth. Their rotations twist space-time in subtle ways. Each extreme environment becomes a chamber in the labyrinth, one where different rules can dominate. The second answer is that our expectations were too narrow. We defined a single path for how these stars should age. The universe has supplied many. To progress through the maze, we turn to the forces shaping these signals. Magnetic fields are among the strongest contributors. They reach intensities that reorganize particle motion, alter photon trajectories, and shape emission patterns. In one corridor, the cold flame thrives. In another, the radio pulse survives below the graveyard. In yet another, the field accelerates particles into a trail of antimatter. These fields do not operate alone. Rotation spins them. Crustal fractures shift them. Interior currents bend them. It is as though the labyrinth walls move with time, rearranging the conditions inside. Gravity plays its part. The weight of a neutron star compresses its interior to densities that turn matter into a quantum fluid. That fluid behaves differently in different regions. Some parts may rotate at different speeds. Others may interact with magnetic structures. When a gravitational wave passes through, the entire star shifts ever so slightly, altering its pulse if only for a moment. These shifts form the watchtower's signals. They reveal that the labyrinth is not just internal. It connects to the wider cosmic landscape. The ripples that shake pulsar timing are born far from our star-filled corridors, yet they reach us through this network of stellar clocks. A visual analogy helps anchor this. Imagine walking through an architectural maze made of glass. Some walls reflect, some transmit, some distort. As you walk, you see reflections from multiple chambers. One corridor might show the shimmer of a cold flame. Another might reflect the pulse of a long, slow beacon. Another might reveal the ghostly blue flash of a transient in the distance. The reflections do not align, but they share a structure. The glass is the universe's extreme physics, refracting signals in ways that seem inconsistent until one sees the pattern. To see the pattern, we compare what the anomalies share: the cold flame, the antimatter halo, the deep timing shifts, and the blue flashes all emerge from environments where magnetic fields and high-density matter interact in complex ways. They come from places where particle cascades, strong gravity, and intense rotation coalesce. They emerge when the star's crust or core or magnetosphere reaches a threshold where previously hidden processes activate. These processes may appear only briefly or may persist for decades. The diversity in timescales is not a contradiction but a clue. It suggests that the labyrinth is not a single structure but a landscape with peaks and valleys, some temporary, some ancient. Still, we must remain cautious. Correlation does not imply cause. The antimatter trail does not automatically explain the flashes. The slow rotator does not automatically explain the gravitational hum. But the convergence of anomalies around neutron stars is not random. Neutron stars occupy a region of physics where small changes can produce giant consequences. A slight shift in magnetic geometry can ignite a beam. A small glitch in rotation can alter polarization. A fragment of matter pulled from a companion can light a flare that lasts days. The labyrinth is built from the sensitivity of extreme matter to tiny conditions. Let us examine one corner. A neutron star drifting between galaxies might once have belonged to a binary. If its companion exploded or was disrupted, the neutron star could wander alone. Over epochs, small instabilities might accumulate. A crustal fracture could expose deep magnetic structures. A fragment of captured gas or dust could fall inward. Under the right conditions, these processes could lead to a brief explosion or flare. Such an event, rare and fleeting, would resemble the blue flashes. If so, the intergalactic flare is not an exception. It is a corridor deep in the maze. Another corridor opens when we consider pulsar timing. The gravitational wave background revealed by the watchtower hints at heavy objects merging far away. These mergers do more than shake spacetime. They seed the universe with energy and momentum. Over cosmic timescales, their influence reshapes the distribution of matter and the formation of stars. Neutron stars that form near regions shaped by ancient mergers might inherit unusual spins or magnetic fields. Their initial conditions might predispose them to behaviors outside the norm. Thus, the watchtower's signals echo through the labyrinth, altering its architecture across eons. A human-scale comparison clarifies this. Imagine a vast library with thousands of rooms. Each room contains a single book. Some books are silent histories. Others are manuals. Others are riddles. As you walk through the library, you expect books to follow familiar patterns. But in certain rooms, you find books that do not follow any pattern. They contain new alphabets. They contain symbols that shift when you touch them. You realize the library is alive, reorganizing itself based on events across the city. This is the neutron star labyrinth. It is a structure shaped both by internal forces and by the universe beyond it. The challenge before researchers is to map this labyrinth. They must trace the cold flame's persistence back to hidden channels in the star's magnetosphere. They must connect the antimatter trail to acceleration zones sculpted by motion. They must reconcile the slow pulses with expected thresholds. They must tie blue flashes to extreme conditions we do not yet understand. Each of these tasks requires patience. Each requires data from instruments that may operate for decades. The labyrinth reveals itself slowly, one corridor at a time. Why does this matter? Because neutron stars are not isolated curiosities. They are laboratories of matter under extreme pressure. They are engines that sculpt galactic radiation. They are detectors of gravity. They are sources of rare flares. Understanding them means understanding the pathways by which energy moves in the universe. It means mastering the physics that shapes cosmic evolution. When anomalies appear, they are not distractions, they are invitations. They point toward regions of theory that require attention. The most striking feature of the labyrinth is its coherence. On the surface, the anomalies seem unrelated, but as we trace them back to their origins, they cluster around common themes: magnetic geometry, particle acceleration, crustal stresses, superfluid interiors, gravitational tides. These themes intersect inside neutron stars. The labyrinth is not a confusing mess. It is a structure built from repeating principles. Each chamber reveals the influence of density, rotation, or magnetism under unusual conditions. The pattern emerges not in individual anomalies, but in how they group. We must acknowledge uncertainty. Some connections may be illusions. Some phenomena may require separate explanations. The flashes may come from interactions unrelated to neutron stars. The antimatter trail may involve multiple sources. The gravitational hum may include contributions from processes not yet named. But uncertainty is not a barrier. It is the compass pointing us through the labyrinth. As long as anomalies exist, theories must evolve. The chapter closes with a final image. The corridors of the labyrinth converge toward a central chamber. In that chamber lies the question that threads through every anomaly. If so many impossible signals lead back to the same kind of star, what deeper structure of physics have we been overlooking in these collapsed suns? Step back from the maze of neutron stars and their impossible signals. Let the corridors fade to dim outlines. What remains is a quiet landscape lit by phenomena that should not coexist. A dead star shining where no fire should live. A cold flame burning through magnetic channels. A wanderer leaving trails of antimatter. A lattice of pulsars listening to the slow tremble of spacetime. Blue flashes erupting between galaxies. Each fragment carries weight. Together they form a challenge to the way we imagine endings in the cosmos. When we look at neutron stars, we look at objects that should belong to the past tense. They are remnants of lives so violent that entire stellar envelopes were torn apart. In our language, a star that has lost its outer layers is dead. Dead things do not speak, do not burn, do not reveal hidden architectures of gravity. Yet neutron stars do all of these. They shine with disciplined clocks. They carve invisible wakes. They light flares that humble galaxies. They sense waves rolling across the void. They become archivists of the universe. Each pulse or flash a record of forces that shape creation. Consider the quiet persistence of the 22-minute beacon. It is a reminder that the universe keeps time beyond our understanding. Our clocks drift. Our devices fail. But a collapsed sun, crushed into a sphere the size of a city, can keep rhythm for decades without pause. It invites reflection. If nature can build such stability from the debris of an explosion, what else might be possible in states of matter we cannot replicate? The beacon is more than an anomaly. It is a lesson in endurance. The cold flame deepens this lesson. It burns without heat in a region where physics should collapse into silence. It shows that energy pathways continue long after our diagrams predict their end. A beam that should fade instead persists. Perhaps the flame reveals a truth we have been slow to accept. Death, in stellar terms, is not the final extinguishing of function. It is a transformation into a new domain where unexpected forms of activity appear. The cold flame writes this with every polarized twist. The antimatter trail draws a wider arc. Here is a star that says nothing, shows no radio pulse, radiates little visible light, yet floods space with particles that annihilate upon contact with matter. The trail reshapes regions of the sky in gamma light. It influences the particle environment near Earth. It participates in processes we once thought reserved for exotic physics. It demonstrates that silence is not the absence of influence. A star may appear quiet and still sculpt the space around it. In the pulsar watchtower, we see another truth. A neutron star can become an instrument for detecting the slow rumble of giants far away. By spinning steadily, Each pulsar turns itself into a clock built from nuclear density matter. When dozens of such clocks agree that space-time is shifting, we accept that distant events have left their marks. The watchtower shows how the universe communicates across unimaginable distances. It also shows that remnants of death can become the senses through which we understand cosmic evolution. Then there are the blue flashes, brief and bewildering. They erupt where no star should die. They shine brighter than entire galaxies for a moment, then vanish without residue. They may signal collisions, disruptions, or transitions so rare that only the most open mind can approach them. They may belong to a region of physics that occurs only on the edges of the cosmic web. They remind us that the universe still holds surprises that elude our most careful theories. Placed together, these fragments resonate. They whisper that the simple narratives we prefer, the ones with clear beginnings and endings, do not capture the full story. Stars do not simply live, burn, and die. They enter new stages where they measure, radiate, accelerate, and transform. Neutron stars become more than remnants. They become the quiet machinery of the cosmos, shaping the interstellar medium, marking gravitational rhythms, and sending signals through the darkness. A visual anchor helps. Imagine standing on a barren plain under a sky without clouds. The stars above seem fixed, yet the air carries faint tremors. The ground hums with a vibration too small for your senses. A light at the horizon pulses in perfect intervals. A distant spark flashes blue and disappears. You cannot name these sensations, but you feel them. They belong to a deeper structure of the world. Neutron stars offer that experience on a cosmic scale. They reveal tremors in space-time. They pulse with impossible discipline. They flash with violent clarity. They tell us that the universe is not silent. It is full of quiet machinery humming beneath the visible layer. There is also a humbling theme. Our intuition about stability, decay, and finality does not apply well to cosmic objects compressed beyond nuclear densities. These stars are sculpted by pressure, magnetism, and gravity in measures that elude everyday thought. In those extremes, matter becomes more flexible, more responsive, more surprising. Even a slight shift in interior structure can rearrange entire regions of space. A minor change in magnetic geometry can create a beam. A small shock can ignite a flare. The boundary between life and death in such objects becomes porous. Reflect for a moment on the paradoxes we encountered. A dead star that shines. A flame that burns without heat. A quiet object that floods Earth with antimatter. A clock that hears gravity. A flare that erupts where no star should be. These are not contradictions. They are reminders that our models are approximations. They work well for familiar stars, but falter in the corridors of the labyrinth. In those corridors, the old rules are not broken. They are expanded. They are joined by new rules that apply only at extreme pressures and fields. One paraphrased line captures this spirit. Every neat boundary we draw in the sky is only a sketch too close to the fire of truth. The realities beneath those sketches reveal complexities we have not yet learned to recognize. Our maps of the cosmos are works in progress, shifting as neutron stars reveal unexpected behaviors. Here at the end, the question is not what neutron stars are, it is what they suggest about the universe that shaped them. If nature produces objects that can shine in the graveyard, burn without heat, and hear waves from ancient mergers, then the cosmos is stranger and deeper than we imagined. These stars are not isolated points. They are nodes in a network of forces. They show that the universe is built from interactions that unfold over millions of years. They reveal that creation and destruction are intertwined. The final image returns to the labyrinth. All its corridors bend toward a chamber where understanding waits. In that chamber, neutron stars are no longer puzzles. They are gateways. They offer a view into the architecture of matter and energy at their most intense. They show us how the universe remembers, how it transmits information, how it transforms the remnants of death into engines of discovery. If the quietest corpses in the cosmos can reshape our understanding of life, death, and the vast machinery between them, what deeper truths are waiting in the unread chambers of the universe?